So I want to remind you all that if you are all still alive after this lecture, that we're going to do the group picture immediately afterwards, so don't run off. Okay, so this is a sequel to my talk on Monday. So I wanted to give sort of a Blur theoretic perspective or parallel story to the various things that we've been seeing here. And so I feel like between when I talked last time and now, we've seen so much stuff that this now feels a little bit antiquated. But anyway, maybe it'll be once we get to something concrete, maybe it'll be nice and relaxing. That's my hope. But we'll see. Okay, so just a schematic of what we did last time. So last time we started off with Legendre link. We get some differential graded algebra out of it by counting some sort of disks of some sort. And then out of this, we can construct augmentations, which are just DGA maps from that DGA to a trivial, the DGA that's just given by the base field and the zero differential. And then out of this, the collection of augmentations gives what I was calling the augmentation variety. So what I'm going to do today is I want to focus on how fillings fit into this picture. But before I do that, let me just say, it's been hinted at very strongly by various talks, but I just wanted to say this parallels the sheaf picture that we've been looking at all week. And so here's a specific but maybe slightly vague way to say this. We can assemble augmentations into a category, so an infinity category. I'm not going to define this, but let's write it. So it's lambda. So the objects of this are these augmentations, and then there are morphism spaces, and there's a differential and higher differentials and such. So this is the way that this is defined. So this builds on work of Bourgeois and Chartrand, but this Dan and I and the other folks constructed this. And on the sheaf side, there is something that should be pretty familiar to you all now, except maybe I will use different notation for it. So I'll write it as SH of lambda, but you should think of this as what Virginia was writing as M of lambda. So this is just this is a sheaf category, which is, so this is a DG category where the objects are, the things that we've been studying, which are sheaves, compact support with micro-local rank, one with singular support contained in lambda. So, in this, so these form a DG category. So before we, you pass to all these fancier things like stacks and such, that this forms some sort of DG category. This was, built on work of many people, but the way that this was written down was this was written down by Chande, Truman, and Sasso. And then there's a so here's a theorem. The reference is, you want to look at this. I may have typos in these archive numbers because I was sort of doing them from, I looked at them on my screen and then I minimized the window and then I would write this down into my notes. So it's just slightly by memory, but there is some sense in which these two categories are isomorphic. They're isomorphic, they're equivalent as and so this sort of explains a little bit of why the types of this M of lambda for instance, positive grades, there's some version of this on the augmentation side, and we actually saw that for the trefoil. And I'll remind you of that in a bit, that particular example. Okay. So what I actually want to do today is I want to talk about the relation to fillings, and this. So the slogan is that LCH is functorial. This should not be surprising to anybody at this stage because this was the case for everything that we've been doing so far. So the setting is now not just that you have a Legendrian knot or link, but you have a let's say an exact Lagrangian cobordism between two such things, and then that's supposed to induce a map between whatever invariant you've defined. So that's going to be true here. And I want to set this up, but I want to actually sort of draw the geometric way that this comes up. Okay, so what does this mean? So firstly, everything I'm going to do, the first people to really seriously write this down were Ekholm, Honda, and Kalman. For the rest of today, I will refer to as EHK. Here's another possibly typo with reference. Okay, so how's this supposed to work? So as what I've already said over there, so we have a Legendrian inside of R3, and then we get this DGA. Okay, so now let's suppose that we have an exact Lagrangian cobordism, which I will now just draw pictorial. So here's lambda plus, here's lambda minus. L. And this is supposed to give us then a DGA map from A lambda plus, the DGA of the lambda plus to the DGA of lambda minus. And this map I'll write as phi sub L. And this is a DGA map. In particular, the chain map. Okay. So I want to explain a little bit about how this works. But to get there, I realized that the way that I defined the DGA last time, it was completely combinatorial, but that sort of obscures the geometry behind it, and obscuring the geometry behind it makes it sort of obscure where this map is supposed to come from. So I'm just going to rewind a little bit and give you a brief synopsis of the geometric definition of the Takanov-Valiashvili DGA. So, and this is, as with everything, I guess I should have done my usual blanket disclaimer at the beginning of the talk, that everything will be more or less correct, but experts will probably find that I've elided over various things, and I apologize. I'm saying this specifically because this is being recorded, and I am aware that various things I'm saying are not exactly true. Okay. Great. So last time when we did the contour definition, what we did was we took our Legendrian, which was in R3, we projected it to R2, and then did stuff there. So the geometric definition actually goes in the opposite direction, which is that we view this Legendrian as living inside of R4 instead, which is the symplectization of R3. So we have this R3 with the Legendrian sitting inside of it. So this was R3 with a standard context structure. And out of this, you can construct the symplectization, which I feel like has also been gestured at various points. So this is a four manifold, which is just our contact manifold crossed with R. And the symplectic form on this is D of E to the T lambda. So T, what is T? T is the coordinate on this additional factor R. And if you do this, then, so this is called the symplectization of the contact manifold, which in this case is R3. And then if you look at what lies over this Legendrian, you get R cross lambda, and it's easy to check that this is Lagrangian with respect to this symplectic structure. So this is Lagrangian. I'll call it a cylinder. So if lambda is a single component, then this is topologically a cylinder. If lambda has multiple components, this is a bunch of cylinders. Okay. Let's see. So here's my cartoon definition of the Takanov-Valiashvili differential gradient algebra. So it's the same. So well, let me write down the important thing, which is the moduli spaces, which will give the differential. So given Rabe chords AI H1 K of lambda K up to 0, I'm going to define the moduli space. I'm going to log this notation today to mean, it's going to mean several different things, and I apologize for that, but it's just, otherwise I have to think of other notation. So this is going to be a moduli space like this, and this is going to be the set of maps from let's do the symplectization. Okay, so now I should remind you of what D2K is. This appeared in the previous talk, but this is a disk in the complex plane with K plus 1 boundary punctures. This is D2 minus K plus 1 boundary punctures. Boundary points. Okay. So this disk is going to map into the symplectization, and its boundary needs to map to this Lagrangian cylinder, so this Lagrangian boundary condition, such that and these are going to be sort of vague, but U is J holomorphic. So for that, I should say that I've chosen some sort of, so choose some sort of compatible. I'm going to write it down here where nobody can see it, and that way, yeah, you shouldn't worry about this too much. There's a compatible almost complex structure on here on the symplectization. And that allows us to define these, just to say that this map here is J holomorphic. So it intertwines the standard complex structure on a disk, thought of as sitting inside the complex plane, with whatever this complex structure is over here. And there's some compatibility condition that I don't want to get into. There's also a technical condition that I also don't want to get into, which is that it needs to be finite energy. Actually, we can say this, right? So this just means that the pullback of the symplectic form of the disk, if you integrate that, you get something finite. Okay, so and near one of these boundary punctures, so I'm going to write this down, but I think it sort of doesn't really make sense until I draw a picture. So near one of these boundary punctures, U is approaching a rate chord, but it's approaching a rate chord of lambda up at t's plus infinity. And the other ones, so near others, U is approaching AJL as minus infinity. So, and I should close the brace at some point. And maybe because the picture is more important than what I've written there, I won't try to squeeze it in there. Okay, so the picture is I didn't use the color. Here's a disk with a bunch of boundary punctures. And this is going to be mapping into so here this is the R direction, this is R cross R3. So this R3 is my June picture is here. Inside of R3 there is the boundary lambda. And so here's the cylinder R cross lambda. And this is mapping into this picture in such a way that its image looks something like this. So it looks like AI into 1. Okay. So it's what it's doing in the neighborhood of each of these punctures is approaching some sort of strip, which is a rate chord cross R cross with the rate chords. And then the other boundary condition was that the boundary parts of this disk, so minus the punctures, need to, so that's these bits right here, that's their images, those need to lie on this Lagrangian cylinder. And let me just note, okay, so that this is a definition of some sort of moduli space of holomorphic disks, and R acts on this by translation. So part of the deal with this almost complex structure is that it's invariant in under translation in this direction here. And what that means is that once I have one of these things, I have a whole R's family of it just by moving it up and down. Great. So now the definition of the Chicano Valley of the DGA is. So I'll write it slightly differently from last time. So you first take the group ring of H1 of the Legendre. And this is now some ring, and then we look at the polynomial algebra over that that's generated by Greg Ford's lambda. Okay. I'm not going to talk about the grading there, but what I do want to do is talk about the differential. And the differential is, so this is going to hopefully looks familiar if you remember the last lecture. You sum over all possible values for these negative n's basically, and look at the sum of all choices of these so that the dimension of the moduli space that I've written over there is 1. Or maybe I'll put it this way. Once you mod out by the R action, this dimension is 0. Okay. So I sum over all sorts such moduli spaces. This condition, it turns out to be some sort of index condition about the gradings of these things here. And now I'm going to sum over disks. I don't know why suddenly I moved from U to delta, but anyway, so we have disks inside of this moduli space. And for each of these things, there is a sign attached to the disk, which we talked about this combinatorial signs last time. I don't want to get to how to define it here. Then you look at the boundary of the disk as a homology class. So that's like these things right here. These are a bunch of paths inside of R cross lambda. So you can project them to lambda. You get a bunch of paths on lambda. Using what's called capping paths, you can close those up so you end up with loops on lambda, and then this is the homology class inside of H1 of the lambda. And then times AJ1 to AJ. Okay. So that's now the definition of the differential. You extend this by the Leibniz rule, and this is supposed to. So this coincides with the combinatorial definition from the first one. Okay, so that is some result that has to be shown, but essentially it boils down to the Riemann mapping theorem this way. John's nodding his head because this is our results with Josh. Great. So now what I want to do is I want to take this picture here, but now I want to incorporate an exact Lagrangian cobordism into this. Now, R cross lambda actually is a cobordism. It's just a cobordism from lambda to itself. But I want to do this in the case where this is not just a cylinder, so it has sort of different ends on top and bottom. So now that's LB an exact cobordism. Okay, so I have to think a little bit. Well, I'll put it this way, so I don't have to think about going. So between n and minus plus. So what does that look like? So this is inside of this symplectization. And it's a picture that I drew there. So here's again the symplectization. So this is across from 1, 3. And now what this actually looks like, if you want to be precise about it, so here's L, here's lambda plus, here's lambda minus. And what L is supposed to be is that it has some compact region and it has a non-compact region. And the non-compact region is supposed to be just a cylinder over lambda plus at the top and a cylinder over lambda minus at the bottom. I won't write that down. Great. Okay, so what I want to do is I now want to so PHK define I'm just copying this BL 1 plus 2A. The nice thing is that now having set up this geometric definition for the DGA itself, writing down this, at least in cartoon version, what this cobordism map is supposed to be is just a little bit of a perturbation of this. So how do we define this map phi L? Again, I think the most useful thing is to give a picture, but maybe I should write down some words also. So let's say that A is a rate chord of lambda plus, and B, I'm going to give them a different letter just because they're now at the bottom. Chords minus, so and so what I want to do is I want to define this map. So I want to say what phi L of A is in terms of these rate chords down at the bottom. And the way I'm going to do that is I'm just going to look at a version of this moduli space, but now in the presence of this Lagrangian cobordism. So so let's define. So now I'll write it as ML just to say that the Lagrangian cobordism is in there somewhere. And now I'm going to not write all this over again. I'm just going to draw a picture. So the picture is going to be version of this. And it's actually the same picture. So really what's the same? But this now sits inside of R cross R3 with boundary, sorry, with Lagrangian boundary condition, which is no. So what this part means is that the boundary parts here are supposed to map it out. So it's very similar to this picture that we did before.
So where do you see lambda minus and lambda plus in, like, do you still see them at the infinite ends, or do
Yeah,
you
you see them at the infinite ends, exactly. Yeah. So this is still the case that up near infinity, this really looks like just the Lagrangian cylinder over lambda plus, and so it makes sense to require that it is asymptotic to a rate chord for lambda plus, and similarly down at the bottom for lambda minus. The only thing that's weird is what's happening in the middle. Great. So here's the map. So the map. This is so phi L of A. So it's going to be a similar thing. So it starts with a generator of this DJ, which is the rate chords of the upstairs Legendre. And then we multiply by, again, there's some sign. Oh no, I didn't need to work on. Okay, so now I'm going to sum over moduli spaces. And now because L is not a straight cylinder, there is no R action on this. It's not invariant under the R action. And so there's no R action, and what we're going to do actually is to look at rigid moduli spaces. So ML A EJ1 J is equal to 0. And now I'm going to take the sum for delta inside of ML same. So it's going to be same deal. So it's going to be the sine of delta, whatever that is. Oops. Delta minus 1. And then times the homology class of the boundary of delta. Yeah, the boundary of delta, which I encourage you not to think about too much. But anyway, this is just some homology class in L at this point. Once it's been closed up, and then times Vj1. And then the EHK tell you that, so EHK says that EL, which just says that EL composed with the boundary up top is the same thing as the boundary down on the boundary. Great. Okay, so I don't want to, I think, spend the time to try to give you intuition for why this is true. If you're curious and you don't know the floor picture already, I'm happy to talk about it afterwards. But we'll just take this on faith. And so what I want to do now is I want to specialize to the case where L is a filling, which means that it has a no negative end, only has positive. Okay, so particular. Suppose L is a filling of lambda, so that's just a cobordism, so exact cobordism, Lagrangian cobordism from the empty set to lambda. Then what we get out of this picture is we're supposed to get a map which usually we write with epsilon, and we'll see why in a second. So this goes from the DJ of lambda to the DJ of the empty set. And maybe the DJ of the empty sets, well, it's still, the base field is still K, it just has no other generator. So this is just K with the zero differential on it. And this is exactly, this is an augmentation. Except that that's a little bit of a crude thing to say, and in fact, you can make it a little bit better by keeping track of these, the homology classes of the boundaries of these holomorphic disks. I guess I didn't say this, but in the original Chekhov-Valley-Ashburn DGA, these homology classes, we keep track of those by the powers of t. So we have a base point and you just count when boundaries of homomorphic disks pass through that base source. So more precisely, the interesting thing is that, so a filling, what does a filling actually give you? So a filling L of lambda gives, so this gives a map epsilon, so I'll write it epsilon L again, except now I'm going to elaborate on what it's actually mapping to. So what it's really mapping to is it's mapping to the group ring of H1 of the filling with the zero differential. So how does that work? So here's a picture of, so here's the filling. Here's lambda, L. And then what this now boils down to is there are no possible rib chords down at the bottom, so there are none of these asymptotics at the bottom. What happens is that you just end up with a disk with a single limb at the top. A rib chord A for here, and then what we are counting is we're counting something like this. So the modular spaces are counting maps that whose image looks something like that. So here this is delta. And what we're saying is that epsilon L of A is a sum over delta in this moduli space, which is A at the top and nothing down at the bottom of some sign associated to delta times the homology class of the boundary of delta. And this again, I'm thinking of this as inside of H1. So as before, it's not actually, the boundary of this is not actually a homology class, right? It's maybe at most the relative homology class here because it has two endpoints. But you can fix this by just, for every rate chord, you choose some sort of catching path that joins the two endpoints of the rate chord together along lambda, and then you use that to close these up so you actually get honest classes in each one. If lambda has multiple components, this is a little bit more fraught, but okay, it can be worked out there as well. Okay, so what this means is that we don't actually get an augmentation to the base field K, but we get an augmentation to this group thing right here. And you can do this a couple ways. One is, well, just like that. But another is to say, okay, so now if I have a local system on L, then that gives me a map from here to K. So, here. So given a local system of rank 1 local system on L, so well, these have been talked about quite a bit now, but just in case you lost track, this, yeah, you can just think of this as a group homomorphism from H1 of L to GL1K. This, we get a map, so K reference L, okay? And so if you compose that with epsilon L, now what you actually do get is you get an augmentation in the way that we were looking at it before. So the conclusion is that, so the conclusion is a filling of lambda equipped with a local system. So I'm just talking about rank 1 local systems, but there's no reason you couldn't do this in higher rank as well. Then you just get maps to matrices, to endomorphisms of K to B and for some n. So a filling equipped with a local system induces augmentation, which is just a point in the augmentation variety. Or if you like, if you don't want to choose a local system, then what you end up with is that it induces a family of augmentation. Right? So a filling induces a family of augmentations. From local systems, rank 1 local systems of L, which again is just into the augmentation variety. And this is, so if L has genus G, this is just K star to the 2G, and this should be looking extremely familiar. So in particular, if so you get a map from here into there, and in nice cases, so in particular, if lambda is a knot, and then oh no, sorry, this was if lambda is a knot. This is true. And then there's a result of Gao and Rutherford. This result that says that this is an injection, suitably interpreted. So this is exactly an algebraic torus chart inside of the augmentation variable. Filling gives lambda gives an algebraic torus chart. The augmentation variety. This is like A star to the 2G inside there. I know this, of course, everybody should say, yes, this is familiar to us, right? This is exactly like one of these cluster charts. Okay, but that's from the Floer theoretic point of view, that's how you get these cluster charts. You start with a filling, that gives you a family of augmentations, and that gives you some sort of chart inside of this augmentation variety. Okay. Great. So I want to, so that this has all been fairly abstract. I want to actually do some concrete examples, but I want to make a couple of remarks, which I think have actually already been, at least part of this has already been stated. So, but just in case, I know that none of you ever got lost in the lectures, but just in case. So one is that, so this is the way of starting. So what this tells you is that fillings give you augmentations. And so you might ask, is the converse true? And the answer is no. So not every augmentation comes from, let's say, an embedded orientable filling. So just for your cultural knowledge, so I think the easiest counterexample is the figure 8 knots. So here's a a version of the Legendre figure eight knots. It's still a triple.
Yep.
I just need triple. Okay. So this is a figure eight knots. So this figure eight. It does have an augmentation. It actually has a unique augmentation. Check. We talked about last time. But it has no embedded orientable fillings. And the obstruction is that. So this is the results. Well, attributes to Chantrenne, but it's a nice exercise in algebraic topology to check. So if lambda is a Legendre knot with filling L, that's embedded and orientable. It actually doesn't even need to be exact. It's just embedded orientable Lagrangian filling. Then the Thurston Benneken. Nobody has actually defined the Thurston Benneken number. Is that true? Okay. So the Thurston Benneken number of a Legendrian knot. So the Legendrian is at every point on it, it is tangents to the contact plane at that point. Right, so the contact planes as you go around the Legendrian gives you a framing of that knot, and the Thurston Benneken number is just the number that is given by that framing relative to the cyber. So this is true that this is twice the genus of L. It's one, and this case has Thurston Benneken -3. It's actually just the right of this diagram here, and pretty clearly there cannot be a surface where this is equal to this. Great. So not every augmentation comes from this, but a lot of them do. So the special case of the families that we've been looking at for the most part in this lecture series are like rainbow closures of positive braids, or maybe almost that, right? These lambda sub betas, and those do have fillings. But this one just doesn't. So let me say that. Okay, so there are various ways to get around this fact if you still want to insist that, okay, I would like to have some geometric interpretation for augmentations that maybe doesn't pass through sheaves. And one way to say it is that it's something else that we have all seen quite a bit is that, well, there's no reason that we need to look at embedded fillings. Well, one could look at immersed fillings as long as they're unobstructed. And also, I should say, immersed fillings also produce augmentations. And so I want to advertise. Here's the results. So it's not super surprising in the context of the other things that we've seen in this workshop, but that's results. So this is originally due to Penn Rutherford for K is 2. And this is the result of June Lee there for arbitrary in general. Says that any augmentation of a Legendrian link is induced by some unobstructed immersed filling. Unobstructed, let's say, oriented. But immersed, let's say the most important.
Question, is there a result then, or do you know if you can deduce the same thing from covariism? Like you have a map between DJ, not necessarily with a field.
Ooh.
The DJ is somebody else, then the covariism also, there's an inverse Lagrangian covariism does the thing.
You mean if I don't use a field as the target profile?
Yeah, exactly. So you have lambda minus, lambda plus, and you have a map DJ of lambda plus and DJ of lambda minus. Do you think either of your strategies could then use it, then there must be coming for an inverse Lagrangian covariism?
I think the thing is, I need to start with an augmented Legendre link, and there is a procedure to resolve that into an augmented Legendre unlink. and the procedure is given by N and Rutherford.
So I agree that, yeah, the precise technique that you use doesn't extend immediately, but the question is, do we think that maybe it could?
I think I have to use like if you consider the coordinate map for the pinch move, like there is it looks like A1 goes to A1 minus S inverse, A2 goes to A2 minus S inverse, and the red chord A goes to S, and this S has to be invertible. It's like if I want like augmentations on the top, if I have augmentations on the top, I want to construct an augmentation on the bottom, such that the new augmentation on the bottom is compatible with the augmentation on the top. Then I have to make sure that at the pinch move, like this ripcord, the augmentation sends that ripcord to some invertible element. Because I have S inverse like in my formula. So I have to invert it. So that's why I didn't do it for other rings. Like I was initially trying to do it for Z, and
The question is not about the ring
Never
or
mind.
field, it's about.
It's about if the cobordism has a minus.
Right, lambda minus at the bottom.
if it has
Still
a
the thing.
if it has a minus N at the
But I
top,
think the answers are very clear. It's like, these could be possible, but their method doesn't.
That's right.
Right.
Yes,
Yeah.
that would be
Yeah.
far outside of the method from our look. Good question.
Great. Okay, so now I want to present to you a simplified version of a combinatorial map that's defined by Nicole van der Kammen in a particular local model of a cobordism, and that local model is saddle cobordism. So here's what it's going to look like. So what will it look like? So now I'm going to sort of reverse to the pictures that I had last time. So here's going to be the XY projection, the projection to the XY plane of some Legendrian, which I'm going to write as lambda plus. And let's suppose that here's a local picture here. So here's a crossing of this XY projection. And let's assume that this crossing, so suppose this crossing is a red chord, so this red chord is contractible. And what that means is that there's some isotopy of lambda plus that keeps the diagram the same, except it just makes the height of this red chord as small as possible, as you like. So there's actually at the end of this, there's some singular Legendre where these two actually get pass through each other through space. So then EHK just by hand they construct a Lagrangian cobordism, exact Lagrangian cobordism from this lambda plus to lambda minus, where lambda minus looks the same except we do this. So there's some cobordism between these two things, which topologically looks like a saddle. And because we haven't been, since the lecture that I was doing, we haven't been thinking about this XY projection. Let me just note that the D4 minus move is an example of this. So 4 minus. So in the XZ projection, which is where the D4 minus lives, that looks like something like this that's replaced by that. But in the XY projection, you just draw this. This actually looks exactly like this. Gets replaced by that. Remember that y from the XZ projection, y is just the derivative of z with respect to x. And then you can check that the ripcord here, which is contractible, is just in the XZ projection, it's this. And so you can see that through a Legendrian isotopy, you can just make this as short as you like. And so that makes this ripcord contractible. Great. So the D4 minus move is an example. Okay. So I'm going to give this ripcord that we're destroying a letter, so I'll call that A. And now let's define. So if B is another ripcord plus. I feel guilty using the same notation. I already advertised I was going to do this, but. And AJ1 and AJK are also chorus. Plus. I'm gonna define this thing here, and now I'm going to write it as, so the moduli spaces we had so far, I had one end at plus infinity and all the other ends at minus infinity. So this is going to be the same thing, except now I'm gonna draw it in this projection, and what that means is that, so remember that in the projection, each of the quadrants around a red chord had signs, so there are 2 pluses and 2 minuses. And so I'm going to sum, and so this is going to be a collection of things. I'm really going to just draw it as a cartoon. So it's holomorphic, this is just immersed disks that have 2 positive corners at A and B. And then some number of negative corners, and the negative corners I'm going to write as, I'm just going to label them around as AJ1 through AJ. So, so with this, we'll do an example. We'll do sort of the canonical example in a second. But with this, then I can define. So now I can define the map. L plus minus. And again, it's going to be a DGA map, so I just need to tell you where it sends the generators. And so I'm actually going to introduce a parameter down here. What I'm going to do is I'm going to decorate this picture down here with 2 additional base points. I haven't talked about base points very much, and I think I don't have time to. So I think I'm just going to draw this, and then we'll do an example. So what I do is I put in 2 base points where the saddle used to be, and one of them I decorate with the letter S, and one of them with the letter minus S inverse. And then what's happening is that this A gets sent to S. And then any other grid chord B gets sent to B plus a sum over all possible AJ1 through AJK. So now sum over this moduli space. And what is going to go in here is just as before, it's going to be some sign associated to lambda, to delta. But this is actually a sign that we know from last time. It's not these signs, but there's also a collection of orientation signs in each of the quadrants that give you the signs in the differential. And this is just the product of the orientation signs of the quadrants of the corners. And then W of delta. For W of delta is just the product of all of the negative corners, AJ1 through AJK. And then where there used to be, so there's one positive corner besides B, which is at A, and that's now going to be replaced by S inverse. Okay, so let's do an example. Example is going to be the profile. So our friend from last time. Base point over here. Here is A1, A2. So there is an exact Lagrangian cobordism that what it does is it destroys the crossings at A1 and A2 in succession. Now there's an S here and an S inverse there. A2 and A3 is still there.
So this map doesn't map into A lambda minus, it maps
Uh,
into A lambda minus decorated, right?
It maps into some extension of A lambda minus that has some additional iterations.
And is what's happening something like you have for every holomorphic disk you had before using this local model, you get a new holomorphic disk on the other side.
That's correct.
It's using the local model to patch them.
That's right. Yeah. That is indeed, that's sort of the concept of the EHK results that. So A1, A2, A3. So A1 gets sent to S. So that this move here, we're destroying A1, that gets it to S. A2 gets sent to. Yeah, A2 plus something, and the something counts disks with two positive corners, and here you can actually see one. There's a disk right here with two positive corners. It turns out that it has a negative sign attached to it, and so what you end up with is just, there are no negative corners, so the only thing that shows up in that W of delta is just S inverse, there's a minus sign. That's the only interesting thing, so A3, there actually are no immersed disks with positive corners at A3 and A1 with any number of negative corners. So A3 just gets sent to A3, that's it. So let's do this again now, but destroying A2. Oh, I should. Since I'm gonna do this twice, I'm gonna label this as S1. That was not where it's.
Okay.
No. One, two, that's one, this. So what has happened now is that this map sends A2 to S2. And now it sends A3 to A3 minus S2. And everything else just remains as it is. So if you combine these, if you concatenate these maps here, what you get is you get A1, A2, A3, there's a T also that's around. So T gets mapped to T, A1 gets mapped to S1, A2 gets mapped to S2 minus S1 inverse, and A3 gets mapped to, sorry. So this is the unknot here, but the unknot has a unique augmentation, which you can sort of see. So this red chord right here, the differential of it is 1 plus S1 times S2 times A3. So there's a unique augmentation, which I've only talked about saddle cobordisms, but there's a cobordism that just fills in unknots, and what it does is it is the unique augmentation. So A3 in this case, what did I say? 1 plus S1, S2, S3. So if there's going to be an augmentation, A3 has to be sent to minus S1 inverse, S2 inverse. So I think if you combine these all, then what you get is you get minus S1 inverse, S2 inverse minus S2 inverse. So we get this map here, and this is a map for a filling of the trefoil, where I've done two saddle moves and I've filled in an unknot. And this actually is an augmentation. So this is a family of augmentations. Oh, this last bit right here, T also has to be sent to minus 1. So this gives us a family of augmentations in the augmentation variety for the trefoil, which I'll remind you from last time turned out to be 1 plus A1 plus A3 plus A1 into A3. Nope, this is the problem. No, 1 plus. You can check my math on this. 1 plus this. So I think if you plug in these things here, then that actually is satisfied. Okay. And this is actually, so this of course should look familiar, because this is one of the charts on this particular augmentation variety. And there's a chart that this is actually a cluster chart. So the correspondence between this and what we just saw in the previous lectures is replace S1 and S2 by capital A1 and capital A2, and possibly fudge with the signs, because I don't know if I got the same signs as before. But in that case, A1 is capital A. Let's put it this way: capital A1 is A1, and capital A2 is so that's S2, so that's A2. I can't do this on the fly. I apologize. Okay. Which, except for this minus sign, this should look familiar, these are cluster coordinates. The sign, the choice of signs is just like some artifact of how we choose dimensions. Great. Okay. So that's the EHK map. And now you can do now you can run the same crank as in the lectures, which is to say that if you have fillings that you want to distinguish, then what you do is you check if they give you the same family of augmentations. And now, you can compute all of this combinatorially. And so, for instance, this is the original way that Echolm shows that the trefoil has at least 5 fillings. So they constructed 5 fillings. They show that they were all distinct by just checking what their family of augmentations was and the augmentation variety of the trefoil. Actually, they were working over the fields and up to, in which case the variety just has 5 points, and this correspond to these 5 fillings. But one thing that the Floor approach does is that this works for any Legendrian. So it doesn't require that we've already constructed a cluster structure on the augmentation variety or on the sheep side or what have you. This will work in any case, and this will allow you to distinguish between exact Lagrange and fillings of particular Legendrians. So in my final 1 minute or so, I think I wanted to advertise a result which then I think Roger will probably build on versions of this later on. So Roger and Hung Hao have this paper where they, I think, were the first ones to construct infinitely many distinct fillings of a particular Legendrian knot or link. And so that was done using, what should we say, using sheaves and clusters, or less. But you can reproduce at least some part of that using Floor theory. And so here's my picture for how this works. So this is just a method of constructing infinitely many fillings of a particular fixed Legendrian. And that is, so here's a Legendrian. This is actually a link. I've drawn it as the -1 closure or something. So this is in the XY projection. And the idea is that starting with this Legendrian link, you can do 2 things. One of them is you could just by hand construct some sort of filling of this by using these saddle cobordisms. And so that I'll call L0. There are lots of choices of this, but choose your favorite one. But then the thing that creates infinitely many is that now we're going to start stacking on top of this traces of Legendrian isotopy. So there's a Legendrian isotopy from lambda m. This should be lambda from lambda m itself, which I've tried to draw here. So what it does is it just takes that box of m crossings and does a Legendrian isotopy where you just push it all the way around the diagram until it gets back to where it started. So you're not touching the white stuff; it's only the pink stuff that's moving. And this is just a collection of Reidemeister 3 moves, and that's nice because the DGA maps for Reidemeister 3 moves are easy to write down. So this is quite easy to calculate. And so what you get out of that is you get this trace of this isotope gives you a map from the DGA of lambda m back to itself. And now you can just stack this on top of itself a bunch of times. So you get just some power of this automorphism. And then you compose it with the family of augmentations that you get by just filling in at the bottom with a fixed filling. And you can do this. You run this process and just check that in fact all of the family of augmentations that you get this way for different values of n, so for different numbers of these stacked cylinders, are all distinct from each other. And so that gives you infinitely many fillings of this particular Legendrian. And if you don't care about this particular one, because what is it anyway? You can construct things out of that. So there's a cobordism from this to like the Legendrian 3 n torus link where n is at least 6. And so that will recover the result of Roger and Hung Hao that those particular Legendrian torus links have infinitely many fillings. Okay, so I've run out of time, so I'll stop there. Thanks.